Hello everyone. Today we'll be discussing about decision trees and how it actually works, how the data is split for a decision tree. So decision trees are nothing but simple if-else condition, meaning consider if it's a whether a player decides whether a tennis match should go ahead or not. So the features present for the dataset is an outlook, temperature, humidity, wind, and depending on this condition, a decision would be made whether to play tennis or not to play tennis. So as I said, decision trace is a simple if-else condition. It'll go and see if my outlook is sunny, and if it is humid, then humidity is normal, then play tennis. Or else if outlook is sunny and humidity is not normal, that is high, then do not play tennis. And if outlook is overcast, always play tennis. So it's an if-else condition, as you can observe here. And to understand, before understanding how this split happens, how decision tree actually works, we need to understand some main concepts. Well, like uh, entropy. Next is information gain. Information gain. Third one is Gini impurity. I'll explain you why these concepts are important. Now, coming to the entropy. First concept is, um, one second. Yeah, the first concept is entropy. Entropy, like depending on the value of entropy, the splits on which feature has to be done is decided. Like the split over here, as you can see, is on outlook. Why outlook? It could be temperature, humid, and wind, right? So to decide that, entropy for each feature is calculated, and how it is calculated is uh, entropy. Consider my predictor variable has n classes: y1, y2, y3, so on, yn. Then my entropy for entropy h of y is given as minus summation of I equals to 1 to n, that is the number of classes, probability of yi into log of probability of yi. Uh, like if it is a two class setting, then n equals to 2, then this can be rewritten as minus probability of y plus log probability of y plus minus probability of y minus into log probability of y minus. So what essentially it means is, for example, in my data set, there are uh, there are 14 data points. So my data points are 14. Of this 14, my positive cases are 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, and my negative cases are 5. So, sorry. So, entropy for this data set will be that equals to minus probability of y plus is nothing but 9 by 14 log of 9 by 14 minus probability of y minus is nothing but 5 by 14 log of 5 by 14, and this value will come down to 0.94. So yeah, so this is how entropy is calculated. And there's something called as an like graph for an entropy, and this graph will be like this. If this is y-axis is the value of entropy, and my x-axis is a probability of y being a data point being a y plus, then my graph would be defined like this, where the peak would be attained at probability equals to 0.5, and that entropy value will be 1, and this is 0 and this is 1, which means when there are equal distribution of classes, it will have a peak value entropy of 1. And if there is any imbalance in the distribution, like if I consider sorry, if I consider there are more negative points compared to the positive points, then my entropy value will be closer to 0. And if there are more positive points and less negative points, then still the entropy value will be less. Like either of the cases, the entropy value will become less. Now, this is entropy, and next one is information gain. One second, let me. Yeah. Next is, say, this is my first topic. Next is information gain. Information gain, IG. My information gain is defined as, like, say, if the split happens on Outlook, then information gain of Y of Outlook is defined as, say, sorry, so if the split happens at Outlook, there are three instances, right? Like sunny, um, overcast, and rain. So, like if it is sunny, there'll be 1, 2, 3, 4, 5. Like there'll be 5 data points here, and here overcast is 1, 2, 3, 4, 4 data points here, and rainy is 1, 2, like 9, and this becomes 5, right? So the information gain is nothing but for Outlook feature is like like these are, in a way, you can see three sub data sets. So if it's given as D1, D2, D3 before any further splits happen, then how information gain calculated for Outlook feature is number of data points for dataset D1 by total number of data points in that data into entropy for dataset D1 plus number of data points for in dataset D2 and divided by total number of data points and entropy at this level. So entropy for dataset D2 plus number of data points in dataset D3 into total number of points and entropy at D3. This is how information gain for a feature is calculated. Next is Gini impurity. Gini impurity is almost similar to your entropy. Only difference being is the formula. Like Gini impurity is also defined as Ig, but G as a subscript. Is nothing but 1 minus summation of I equals to 1 to n probability of yi whole square. Like in my entropy calculation, it's probability of yi into log of p into log of probability of yi, right? Here we don't have the probability, rather it will take a square, it will square the inside summation value. So why we have to go to Gini impurity when we have entropy? Like we ideally prefer a Gini impurity over here over entropy because computational time will be less for Gini impurity when compared to entropy, mainly because entropy has a log term inside it. Okay, and this will have a peak value of Gini impurity will have a peak value of 0.5, whereas for entropy it is 1, right? So if you see this graph, this will be the Gini impurity graph, and this value will be 0.5. Okay, so this is entropy, and this inside part is Gini impurity. Now, how to construct a decision tree? So, how a decision tree is built using the concepts of entropy, information gain, and Gini impurity. So, what happens is first we will calculate the entropy for the dataset D that we saw it as 0.94, right, just a while back. So now, like as you can see on the left hand side here, the first split happens with outlook feature. So how is that decided? How that's decided is, so sorry, we would calculate entropy for each and every feature. Say if we decide to split by outlook feature, imagine, then it has three cases, right? Sunny, overcast, and rainy. And this has two positive, and if it's sunny, then one, two, three, four, five, four, and five. Right? Of these five data points, like two are positive and three negative, right? And for overcast, it is four positive and zero negative. And for rainy, it is two positive and three negative. So what happens is for like and you know we define it as D1, D2, D3, right? Different data sets. We will calculate entropy for each of these data sets, and we uh, add them up, like uh, entropy for D1, entropy for D2, and entropy at level D3, and we'll get weighted entropy for outlook feature. Similarly, say for temperature, we will again calculate the entropy. So for temperature, we know it's hot, mild, and cold, right? Hot, mild, and cold. So when it's hot, we have uh, one and two positive and two negative. And when it is mild, we have four positive and two negative. And when it's cold, we have three positive and one negative. Similarly, for this, we will calculate a weighted entropy. Okay, entropy, and similarly for humidity. One second, let me rewrite this. Similarly, we'll calculate entropy for humidity feature. So for each of these features, what will be the weighted entropy we will calculate, and which has the highest weighted entropy value, that would be considered as the first parent node. Similarly, after the split happens on the parent node, we will recalculate again the entropies for, say, other features, say humidity, temperature, and wind. Then say if over here if wind has the highest information gain, then we decide to split on the next level on humidity feature. So this is how decision tree algorithm works internally. One second. And uh, how deep we can go for uh, decision trees. Like if we go to the minutest levels, then say if there are 100,000 data points, okay, and if we go to the minutest of levels till we get two data points left at the end, that it will have very large depth, right? Very large depth. And because of this, we will have overfitting issues. And if depth is small, depth is small, then we'll have underfitting issues, right? So here our depth is the hyperparameter. And one more thing, for say logistic regression or linear regression or SVMs, we said the features have to be standardized, right? But for decision tree, we don't have to standardize the features because the split happens on actual values. Say it splits on sunny. If it is a numeric value, say if age is less than 50, then my parent or leaf nodes can be this actual value for that feature. Okay, that's one of the important differences between decision tree and other algorithms.